So far we have discussed techniques of electrostatic problem solving. Now in this class we will look at solution of Laplace's and Poisson's equation. These problems are typically classified as boundary value problems. You will soon see why they are called as boundary value problems. Now we have of course used Laplace equation earlier when we were calculating the capacitance of certain structures, like for the parallel plate capacitor we have solved Laplace's equation in one dimension and then proceeded to find out the capacitance of that structure. We called it in fact the V method of finding the capacitance of that particular structure. We have also used Laplace's equation in that sense of solving it and calculating the capacitance when we considered potential of a coaxial cable, right, sorry, capacitance of a coaxial cable. However, at that point we were not really talking anything formally about Laplace's equation, whether the solutions that we found were the only possible solutions that we could find, or if that is the only possible solution, under what conditions will that solution be unique. Okay. So this question is very important because you might, for example, have a situation where two of you might work together, or sorry, work separately and actually get solutions of Laplace's equation with a given boundary conditions. Now what is the guarantee that these two solutions are going to be different, right, if they are same or if they are different. So if they are same, then it is good, because no matter what method you apply to attack the problem, you will always end up with a unique solution. However, if the solution is not unique, that is there is no guarantee that the solutions obtained with different approaches are unique, then there is really no hope of solving such a particular problem, right. So we will look at today a theorem which tells us the conditions that are necessary to guarantee that the solution of Laplace's equation that we find by different methods. By different methods we not only mean by different mathematical methods. There could be methods such as experimental methods, you know, the ones that we talked about by drawing the field lines, and then from there, you know, you can actually experimentally determine the field lines and from there try to proceed to find the capacitance of a structure, if that is the problem that we are interested in. Or it could be numerical method. So you apply a numerical method and then you find the solution which fits the boundary conditions very well. It will also satisfy the corresponding equation, Laplace's equation or Poisson's equation. So if you solve these problems in two different methods and if the solutions are not going to be unique, then the situation is pretty bad for us, right. However, if the solutions obtained by different methods are going to be the same when they are applied to the given problem, then it is good, because you find solution in one method which might be easier to evaluate compared to another method, then you are guaranteed that you have actually solved the problem and you will be confident that there is no other solution that is possible for given scenario, the problem plus the boundary conditions. Okay. So we begin with Laplace's equation and explore what are the conditions that are necessary for this equation to have a unique solution. So if you recall what was Laplace's equation, Laplace's equation was a partial differential equation. This del square is in fact called as the Laplacian operator, and this operator operates on a scalar function or a scalar field V, okay. And for Laplace's equation the right hand side is equal to 0, and for Poisson's equation the right hand side is actually given by the volume charge density at that particular point divided by epsilon. I am going to assume that the medium that we will be working with is all uniform dielectric, and this dielectric that we are going to assume will also be linear, isotropic and homogeneous. By linear, isotropic and homogeneous, I can what I mean is that the dielectric will be linearly responding to the electric field, therefore it can be characterized by a simple susceptibility parameter, okay. By isotropic I mean that the properties of the dielectric are independent of the direction of the electric fields that we apply, so epsilon is again just a scalar. And by homogeneous we mean that the dielectric properties, that is for example the polarization, would not be a function of the spatial coordinates. It will not, for example, if you take a slab of dielectric, the epsilon value here will not be different from the epsilon value at any other point in the slab. So essentially what it allows us to do is that replace those polarizations by the relative permittivity epsilon, and as I mentioned to you, epsilon r, the relative permittivity, has to be multiplied by epsilon 0, the permittivity of free space, in order to give you the full permittivity epsilon, and that is what the notation that I am going to use. Anyway, Laplace's equation is much more solvable than Poisson's equation, or occurs much more naturally than Poisson's equation. So we will be concentrating mostly on Laplace's equation. So we will hardly be having any use for epsilon that is not given constant, that is not a constant. Okay. So with that in mind, let us explore what are the conditions that are necessary for this solution that we obtain of the equations to be unique. Okay. So this solution or the uniqueness of the solution is actually captured by what is called as uniqueness theorem. Okay. We will be dealing with this uniqueness theorem in a qualitative way. We will not be considering the mathematical problems that might really, the real mathematical problems that might arise, but for our purposes the theorem will be developed sufficiently so that you will be confident that if you solve Laplace's equation or Poisson's equation with a given boundary condition, then you have obtained only one solution, okay, and that solution is going to be unique. Okay. So what is uniqueness theorem? To develop that, consider first a surface S. Okay. This surface S also bounds a particular volume, okay, encloses a particular volume, and for the moment let us not put any sources inside. Okay. So we have no sources, no conductors inside. That second part of the theorem that we will be developing will actually have some conductors inside. Okay. For now there are no conductors or no charges that are specified inside. So clearly this is a situation where we can apply Laplace's equation, because del square V will be equal to 0 throughout this surface or throughout this region, which is characterized by the surface S and the corresponding enclosed volume V. Okay. Of course, the Laplace's equation is just that. You need to supplement this equation by certain boundary conditions. By boundary conditions we mean the values of the potential at the boundary. So if I specify the value of the potential at the boundary, okay, so V at boundary, then I will be able to solve this equation and obtain a solution. Okay. Otherwise the solutions that we obtain will be quite general. If you are confused about what this boundary and what the solution that is not, that requires the boundary condition, just consider an analogous equation, say d square x by dt square, which could for example represent the acceleration of a particle under the force or under no force. So if I have this equation d square x by dt square, where x is a function of time, if this is equal to 0, then if you integrate this equation once, you get dx by dt to be a constant, right, and you integrate once more, you get x of t, which is the displacement for example, to be a t plus b. Now this is all the solution can tell you. Now unless you specify the initial conditions, like you specify what would be the initial position at time t is equal to 0 or at any other convenient time, you also specify what would be the value of dx by dt at time t equal to 0, you will not be able to evaluate these two constants a and b. So to evaluate the constants a and b of this solution, which is a general solution, you need the initial conditions. Okay. Now in potential problems what we typically find is, okay, in a case of a parallel plate capacitor, which we will discuss later, you have a potential of the top surface kept at some V0, potential of the bottom surface is at 0 because I am going to ground this one, and I am looking at applying Laplace's equation in the region in between, right. So it will eventually reduce itself to a nice differential equation, and when you solve the differential equation in the region here, right, in the region between the top and the bottom plates, you will end up with two constants, and to find the values of those two constants you need to know the value of the potentials at the boundary. Okay. Here you were talking about initial condition because the variable was time, and it is natural to think of them at time t is equal to 0 or time t is equal to infinity as initial and final conditions. However, in case of problems that are not time dependent per se, but they are dependent on space, okay, the variable, the independent variable of this one is space, then it is natural to talk about boundary values rather than initial values. So this is called as an initial value problem, this is called as a boundary value problem. They are not mathematically same because there exists some important differences between the two. In the initial value problem, you actually are given the values of x of t and the corresponding derivatives, okay. at a given point in the solution, and then your objective would be to find the solution at all later points. Okay. So, you start with one points over here and then you start moving towards the values of that x of t, for example, at different values of time. So, you just start at one point and then you try to move, then you move to the other points trying to find the solution everywhere for time t greater than 0. On the other hand, in a boundary value problem such as a parallel plate capacitor over here, I know what is the boundary here or the potential value here at this boundary, and I know the potential value at this boundary. Okay. And my objective is to find a function that fits into this boundary satisfying the given equation. So, there is no marching, you are not starting at one point and marching over to the next point. You actually have a function which is in between, and then you are trying to fit a function that satisfies the boundary conditions. So, they are not the same, but in some of the numerical methods of solution that we will be taking up, you will actually convert a boundary value problem into that of an initial value problem. That is something for later time. So, let us not worry about that for now. The important point of the last few minutes of discussion was that it is necessary, in addition to specifying the equation that governs the situation of the problem, it is necessary to specify the corresponding boundary values. Okay. So, these problems are called as boundary value problems, and since we are looking at electrostatic case, these problems are called as boundary value problems in electrostatics. Okay. So, with this digression that we have made, let us get back to the original problem. Like we have a region of space that is described by the surface S, which encloses a volume V. Within that surface we are applying Laplace's equation, and we apply the Laplace's equation, we find a solution. That solution must now fit into the boundary values that we have specified. The question we were asking was, if I give you two such functions, okay, or two such solutions, will they be unique or not? That is, will they be equal or not? If they are equal at all points in the space including the boundaries, then the solution is unique. You cannot have two solutions which are not equal everywhere including the boundaries, but they satisfy the same set of equations. Okay. All right. So, to develop that we need some results from vector calculus. So, let us look at that, and in the following what I will do is, instead of talking about V, I will use a function psi. Okay. Psi is, I want to use this one because I want to, not that because V is potential and psi is a different thing, psi is also the same kind of function, but I want to be little more general, and therefore I am considering a potential psi. This generality may not be necessary at this point. Okay. However, when we talk of uniqueness theorem in the time varying case, we will see that this electrostatic potential needs to be replaced by a different kind of potential. Okay. So, in that case, it pays to us to be little more general. So, I am going to switch the notation from V to psi. Okay. And I want to use, or I want to get a particular result from vector analysis, and that result can be obtained by looking at this quantity. So, consider divergence of psi gradient of psi. Okay. We have seen this earlier when we were developing, I believe, curl equation or something when we were developing this. So, we have seen this vector identity earlier, right. So, if you recall, we had a scalar function f and a vector field A. Okay. And if you multiply the scalar function with a vector function or a vector field, you still end up being with a vector field, and del dot of f A, which is this quantity, divergence of this quantity f A, is given by f del dot A plus A dot gradient of f, right, because gradient of f gives you the vector field. When you dot that with A, you will get a scalar, and everything else is a scalar now. So, this is the vector identity that we are going to use in this context. So, you have divergence of psi, gradient of psi. Okay. So, this would be obviously equal to psi del dot gradient of psi, because the vector field A is gradient of psi for us. Okay. So, psi del dot gradient of psi plus gradient of psi dot gradient of psi. Now, from the definition of Laplacian operator, I already know what is this term, correct. I know what this term is, and that is nothing but del square. So, I have psi del square psi plus del psi magnitude square, because A dot A is magnitude of A square, right. So, this is the quantity that I have, and if you look at this quantity, you will immediately recognize that this first term has to be equal to 0. Why? Because in the surface that I am considering, the Laplacian equation tells me that del square of the potential is equal to 0, and since psi is essentially potential that we are considering, this fellow must be equal to 0. So, 0 multiplied by psi is 0. So, this entire term is equal to 0. So, what we are left out with is a quantity which is completely positive and greater than or equal to 0, right. It can at most be equal to 0, but it can never be negative. Why cannot be negative? This is magnitude square. Whenever you take magnitude of a particular number, that number will always be positive or at most equal to 0 when that number itself is equal to 0. Okay. Starting from this relation del dot psi gradient psi is equal to del phi square, the next step for us would be to integrate over the volume that this region of space is enclosing. So, if I integrate this over the volume, I get, on both sides I have to do this integration of course. So, I integrate this one over the volume, okay. And if I do that on the right hand side, I am integrating this quantity gradient psi square dV over the volume V, okay. Now, I know what is divergence theorem, Gauss's divergence theorem, which allows me to convert an integral of this nature, okay, into a surface integral, right. So, I can convert this into a surface integral, except that the surface has to be closed. If you are unsure about this, recall how we used this relation for developing the point form of Gauss's law. So, you had del dot d dV integrated over the volume. This was equal to the charge that is enclosed in that volume, but this quantity del dot d dV was actually can be replaced by this surface integral of the flux density, right. So, this was the divergence theorem that we used, and using this divergence theorem, but on this quantity I can replace the volume integral of divergence of a quantity by a surface integral of that quantity, okay. So, this right hand side does not change, it remains the same. So, I have del psi square dV. Now, we come to an important part in this theorem, okay. If you look at the left hand side, you have some surface area, I am not showing the entire surface. So, this is the surface that we were considering and the corresponding volume that this surface encloses, okay. ds bar is a vector surface element, right. So, if you consider on this surface, this small patch, this small patch that I am considering as the differential surface element ds, okay. This surface element has an area of ds, but it will be pointing in the direction that is normal to the contour here. The surface has a certain contour, and normal to that contour is the normal to the surface, and the vector surface element ds bar is actually given by n hat ds, that is it has a magnitude of ds, the differential surface area of the surface that we are considering, okay, at that particular point, but it would be pointing, the vector element would be pointing normally to the surface contour, okay, and that is given by this n hat direction, okay. Now, go back to this expression over here, the left hand side has a closed surface integral psi gradient of psi dot n hat ds, okay. The dot operation is actually happening between this del psi and n, right, because that is the vector and this is the vector that you have. So, the dot product is happening between these two elements, okay. If you recall what was this del psi is, right. So, del psi is essentially the electric field, it is proportional to electric field, there is a minus sign somewhere, but that is not really important for us. What is important is that this del psi is proportional to E, and in a situation where I am considering the material medium properties to be described by a constant epsilon, okay, then if I multiply this one by epsilon, what I get is epsilon del psi to be epsilon E, which is nothing but the flux density d. Okay. Now, the flux density d could be coming out in any direction. Okay. So, if this is my flux density d, it could be coming out in any direction on this surface element ds. So, then d dot ds will simply tell me what is the normal component of the flux density d. Okay. So, this del psi dot n is actually the normal component of the flux density that you are looking at, of course, after multiplying by epsilon. So, it is clear that even if it is not dn, if the material medium is there, then it would be proportional to En. So, this del psi dot n could very well be a quantity which is En, the normal component of the electric field at that surface area. Okay. So, this is one thing, you just keep this one in mind, we will be requiring it after a certain time. There is another interpretation over here. Okay. Consider the parallel plate capacitor that we talked about, right. So, I have a parallel plate capacitor up here. I know that the electric fields would all be uniform, assuming that the plates are quite wide in width and length compared to the separation between them. So, the electric fields would all be vertical and would be pointing downwards, right. So, what is, if I consider this as my surface area or a small area around this one as a surface area, and let us say I place the capacitor in x direction, okay, that is the plates are separated at some x equal to a and x equal to 0. Okay. So, this is the two plates, sorry, I should place the top surface at x equal to 0 and the bottom surface at x equal to a. Okay. So, since the direction of x I assumed was downwards. So, what is the normal to the top surface of the elemental area that I have considered? The normal is actually along x direction, correct, and what is gradient of psi? Okay. Well, one interpretation was in terms of the electric field. So, clearly that should give you the normal component of the electric field, but that is one thing. If you expand gradient of psi itself in the Cartesian coordinate system, you will see that there are terms with y and terms with z. Okay. Let us not worry about those terms, because when you take the dot product, these terms will be left out, right. So, you have del by del x of psi in the x direction, and when you take the dot product of del psi with the normal to the surface, which happens to be along x direction, now you get del psi dot x hat to be del psi by del x, right. So, in general, if the normal is along n, what this quantity del psi dot n is telling you is, so let me highlight this one. So, this del psi dot n is actually giving you the derivative of the function, the potential function psi with respect to the normal coordinate, right. If n is any general direction for the normal, then del psi dot n is this del psi by del n. Okay. Very interesting. Now, I can rewrite that integration over the surface as the closed surface, okay, as the closed surface. I have psi here, and del psi dot n can be replaced by del psi by del n ds. Okay. So, whatever the surface that we were considering over this entire surface S, this is the integration that we are performing. Okay. The surface has to be, of course, closed. Now, look at what is happening inside. You have potential psi, you have the field del psi by del n, at least the normal component of the field del psi by del n, and there is a surface ds that you are considering. Now, if I imagine that this surface is not just any surface, but some sort of a spherical surface. Okay. So, this must be a spherical surface of certain radius small r, okay, having a radius r measured from some origin. Okay. Then the surface area would actually be proportional to r square, correct. The surface area of a sphere is essentially r square. Now, I ask you this question, when will this integral go to 0, or when will this contribution of this entire thing go to 0? Well, I cannot just say this to be 0 at a particular value of r. My qualifying condition is that if I start increasing the radius of the sphere to infinity, that is, imagine that I take a sphere and then keep on increasing this distance go to infinity, then when will this quantity be equal to 0? It will be equal to 0 provided this psi del psi by del n go at least as 1 by r cube, correct. It must go at least as 1 by r cube, so that when you multiply this 1 by r cube by r square, which is the proportionality factor for the surface element, surface area goes as r square. If this product goes as 1 by r cube, then the product goes as 1 by r, and in the limit of r tending to infinity, 1 by r goes to 0, and your integration would essentially go to 0. So, in other words, on the boundary, right, the potential times the normal derivative of the potential, this is called as the normal derivative of the potential, at least in my book. So, you can see that if this product goes at least as 1 by r cube, of course, it can go as 1 by r power 4, it can go as 1 by r power 5, it can go as any other higher order term, but it must at least go as 1 by r cube. Of course, it can go as 2.1 and so on, but let us just focus on these terms going as integer values. Okay. So, in this situation what I have is the contribution of this integral over the sphere of radius tending towards infinity will turn out to be equal to 0. Now, this is something that you have seen and you have experienced it when we solved electric fields earlier. Consider a point charge. How does the potential of a point charge go? If the point charge is q, the potential of the point charge is q by 4 pi epsilon r. So, the potential is going as 1 by r. What about the electric field of a point charge? Well, you can take the gradient of the potential, or you know already from Coulomb's law that the electric field goes as 1 by r square. So, the product of this point charge potential and the point charge electric field go as 1 by r cube. So, if you now imagine a sphere of radius r, then on that boundary of the sphere the field is actually 1 by r, and as the boundary starts increasing, in other words as the sphere radius starts increasing, this 1 by r term keeps going to 0. So, you will be integrating over an infinite radius of the sphere, but the values of the fields at each point will essentially be equal to 0, so that the total contribution to the integral itself is 0. This is very crucial. So, the point that we have made is that the potential must go as 1 by r at least, then the gradients of the potentials along that normal direction would go as 1 by r square, okay, at least on the spherical surface, and for all practical purposes this works out very well. So, the conditions at infinity, that is as r tends to infinity, is that potential must drop to 0 and this del psi by del n must drop to 0 even faster than the potential thing. For a point charge it works out very well. For a line charge, when we talked about finding the potential of a line charge, we found that I cannot take infinity as the point of reference for a line charge, and the reason is precisely because of this. The potential of a line charge, an infinite line charge I am talking about, does not go to 0 as you go towards infinity. Why? Because the potential is some log of r, and log of r actually increases towards infinity, does not diminish towards infinity. So, it is pretty bad in terms of that one, and you can see why this is not going to infinity, because this is log of r, not going to 0, because this is log of r, the potential is log of r, the field is 1 by r. So, when you multiply them, at most they would cancel out each other, right. Log of r for very large r is something, in fact they will not really cancel out each other, but you can think of them as being cancelling, large quantity, inverse quantity essentially multiplied together at large values of r would be as a constant. Okay. When you multiply that with the surface area, that is r square, you will see that the total has actually jumped up to r square, that is the product has jumped up to the power of r square at least, and when you integrate r square over in an infinite radius, that fellow will diverge. So, essentially giving you non-zero value for the contribution of the sphere. The same thing happens in the field of a plane sheet of charge, which is infinitely everywhere, okay, because there the potential goes linearly with respect to the distance, the electric field does not even vary with the position, it will remain constant, it will not diminish at all, right. Well, these problems, true, they are mathematically not very nice because they are going off to infinity and their behavior at infinity is not very nice, but those situations are also unlikely to occur. I mean, how much work you require to actually assemble a line charge of infinite length, even if the density of the line charge would be some non-zero finite value. What would be the total charge on that infinite length line? It would be infinite. Similarly, if you cannot actually fabricate an infinitely large plane charge, the plane sheet of charge. So, it is just not possible in practice to get to those situations. Mathematically, you subvert those problems by postulating that the fields are not required to go to infinity at that stage, but they have to go to infinity at a point of reference. Okay. So, there are certain niceties, certain subtleties of this theorem which we are not talking about. So, as I said earlier, but for most applications this theorem works as long as the potential is going as 1 by r and the field is going as 1 by r square. Okay. So, let us come back to this. The whole point of motivating this one was to show that the left hand side of this equation, this equation which I have, can be made equal to 0. So, this equation, the left hand side goes to 0 as r tends to infinity. What about the right hand side? Well, if the left hand side is going to infinity, that simply means that the volume integral of this quantity del psi square dV must also be equal to 0, right. On the sphere of infinite radius, this must certainly be equal to 0. Okay. Now, let us get back to the potential function. Now, let us say that psi 1 and psi 2 represent two solutions of Laplace's equation, which has been found by two different methods. For example, psi 1 was found by you, psi 2 was found by your friend. Okay. Now, because of the linearity of Laplace's equation, this difference psi 1 minus psi 2, which we will call as psi d, is also a solution of Laplace's equation. Okay. Because of the linearity of Laplace's equation, the difference of the individual solutions are also the solution. Okay. And this solution must be valid everywhere. Okay. So, this expression is completely independent of what type of potential function I choose. Okay. So, I can put this psi d into this expression and see that this del psi d gradient square dV must be equal to 0. Now, the only way this can happen is when this gradient of the difference potential is equal to 0, which immediately tells you that this psi d must be equal to constant, right. So, only when there is it is a constant, then the gradient of that constant, which is essentially the slope of that surface, would be equal to 0.